Since we just discussed probabilistic cloning, I'd like to now move on and discuss approximate cloning, and we're going to talk about that in far more detail. So this is the basic circuit for approximate cloning. I have a qubit psi that I want to copy, and then I have an auxiliary 2-qubit state that is going to tell the circuit how to distribute the information about psi. So each line is a qubit going through the circuit, so there are 3 of them altogether. And these objects are these are C0 gates. And let me just remind you what a C0 gate does. So it's a 2-qubit gate. And so there's 1 qubit up here and 1 qubit down here. So what happens is that if I put a 0 up here, nothing happens to the qubit down here. I'm going to write out the full list of things that can happen. So if I start with 0, 0, the 0 up here, which is what's called the control, and this is called the target. So if the control is a 0, nothing happens to the target. So what would come out would be 0, 0. So that's the probably about the simplest case. So if this is a 1 down here, let me just do it like this. It's a 1 instead of a 0. What's going to come out is again a 1. But suppose now that instead of 0 on the upper line, I have a 1. Then things are going to be a little different. So now what's going to happen is it's going to flip the bottom qubit because the control is a 1. So if it's a 0, it doesn't do anything to the bottom qubit. If it's a 1, it flips the bottom qubit. So if this is a 0, what's going to come out, and again, nothing happens to the control qubit. It's just going to be 1 there, but this is going to get flipped. And if this is the 1, nothing happens to that, but if this is the 1, it's going to get flipped, and I will get a 0. So now I have 4 of those things in this circuit. So we're going to have to sort of sit back and analyze what's going to happen. Now what I'd like to do, I'm going to use 2 different states here, which I could call either control states, or I'm going to be calling them later program states. So let me just start with that terminology now. And the first one I want to put in is the following. I'm going to let my program state equal, I'm going to call it C0, 0. And that is going to be equal to 1 over square root of 2 times 0, 0, plus 1, 1. So let's see what happens. The idea is we're going to put this in down here, and in the top one, we're going to have the psi. So what we're going to have, we're actually going to have 4 terms, because this is going to get multiplied by that. So we can check and see what happens, for example, when we put in a 0 on the top and this thing in the bottom. So let's do that. So I think I could probably do it without having to draw everything. So let me call this A, B, and C. So I'm going to put in a 0A, and then I'm going to put in a 0B and a 0C. So what comes out? So this is the input. And then something's going to come out. What's going to happen? So the A is a 0. So that's the control qubit for these 2 C0 gates. What that means is that at least in the first half of the circuit here, nothing is going to happen to either the B or C qubit. Now, then the B and C qubits go along and they become the control. So at this point in the circuit, the state hasn't changed at all. So now the B and C qubits become the control. So the B qubit is a 0, so that's not going to do anything to the A qubit. And the C qubit is also a 0. That's also not going to do anything to the A qubit. So this is kind of boring. So what's going to come out is the exact same state that went in. So that's one of the possibilities that we have to look at. Well, we also have to look at, let's also look at the 0 with the 1, 1. So what's going to happen there? Well, as before, the A qubit is the control up for the first half of the circuit, and it's a 0, so that means nothing's going to happen to the other qubits. So by the time we get to here, the state hasn't changed at all. Now interesting things are going to happen because the B and C are both 1. That means they're going to flip the A. But notice what happens. So the A is coming along here, it's a 0. The B flips it, turns it into a 1. And then it cruises along here. And then the C qubit also flips it, so it flips the 1 back to 0. So again, what we get is the same state that we started with. All right, so now that's 2 out of the 4 possibilities. Now let's see what happens if instead of the 0 in the A qubit, I have the 1 in the A qubit. And then we're going to have 0 in the B and 0 in the C. Okay, now this is a little more complicated. So let me do this one in 2 pieces. All right. So first, what happens is we've got the A as a 1, the B is a 0, and the C is a 0. So that the B and C are both going to get flipped. All right. So by the time we get to the middle of the circuit here, let me call this middle, we are going to have the following state. I'll just put middle up here. So we said that the A being a 1 is going to flip the B and the C. So by the time we get to the middle, I have a 1A, a 1B, and a 1C. Now, so now what happens after that? Well, nothing's going to happen to the B and the C because they're now the control qubits. And so they're going to flip the A. So the A is starting off as a 1. It's going to get flipped once, so that'll make it a 0. It's going to get flipped twice. That'll make it back to a 1. So this is simply going to be okay. Just double check that. So that is a 1 and gets flipped twice, so that looks good. So this is end. And then the other thing we have to check is 1A, 1B, 1B. So I mean, I'm just taking this times this in each of the 4 possibilities. So what happens now is, so we start with A in the 1 and B and C in the 1. So they're both going to get flipped by the action of the A. So in the middle, I'm going to get a 1A 0 and a 0C. Okay, now the B and C qubits are now 0. So that means that nothing is going to happen after that part of the circuit. The A qubit is not going to get flipped because the B and C are both 0, and the B and C are just going to stay the same. So this will simply give me so now we've analyzed what can happen with these states, and now we have to put everything together. So let's see what we're going to have. So we're starting off with the 0A qubit multiplied by alpha. So if I put all of this together, I'm going to have the alpha is going to multiply this term and this term. So let me try to squeeze it in at the bottom. So final okay, and I also have to put in the 1 over square root of 2, which I'll do in a second. And you'll notice that that state is simply multiplied by 0, 0 plus 1, 1. Okay, so that takes care of the first term up here. What about the second term? So let's see what. So the second term is multiplying to 1, so that's these two. So we're going to have the 1 is common to both. So I'm going to have plus beta 1, okay? And you'll notice I'm going to have 0, 0 plus 1, 1 again. So I'm going to have 1 over root 2 times 0. B. Okay, so if I take a look at that, what do I have? The BC terms are exactly the same, so I can factor them out. And I think what I will do is just briefly write out up here what I've got. So you've got the A0 plus B1 times the C00 state. So what's coming out here is just psi A times. So what did this circuit do? It did precisely nothing. So you'll notice that we started with the A up the psi in the A line. It came out in the A line. We started with C00 in the BC line. It came out in the BC line. So this might look like is a really stupid thing to do, but it will turn out to be useful when we get to the next step. So let's just see what has happened here. So essentially, the quantum information that we're interested in doing something to is in the A line. And what this particular program state did is it kept it in the A line. Now, if we can find another program that moves the psi from the A line to the B line, then maybe we can sort of put the two together and have some of the quantum information about the state in the A line and some of the information about the state in the B line, and that will give us our clones. And that's in fact exactly what we're going to do. So let's move on to the next step and look at a different program. I'm not going to go through it in as much detail as I did this one, but I will tell you what it does and then how to put that program together with this program, and then that will actually allow us to do an approximate cloning. Now we're going to go ahead and look at a second program state and see what it does. And in this case, I'm simply going to tell you what it does, because we worked out in detail how this circuit works. You just apply all the same rules that we just applied to the new program state, and you will get the final result. So we're going to choose a program state now that looks like this. And I'm going to call it psi0x. And it's a product state. It's going to be equal to 0 times tensor product square root of 2 times 0 plus 1. The reason for the name 0x is where the first state is 0, and the second state is something that is often called a plus x state because it's an eigenstate of the sigma x operator, the Pauli sigma x operator. So what happens when I put in this program state? Well, it does exactly what I suggested we want to do. It produces a output state where the psi is now in the B line, and then it's times 0, 0, not 0x, in the A and C lines. So what's happened with this particular program state is that it's moved the quantum information from the A line down to the B line. That means that if I somehow put these two states together, one puts out the quantum information, the first one we looked at puts out the quantum information up here, and then the one that I have up here now puts the quantum information out in the B line. So what we're going to do is put the two together. So what do I mean by that? So I'm just going to add them. So my new program is just going to be equal to some constant C0 times the first program plus some constant C1 times the second program. And I should probably put these C's in down here. So that's what we're going to put in. We're going to put in the psi, and we're going to put in this program state. So what are we going to get out? What we're going to get out is that, I think I can put it over here is probably the best place. So we're going to start with psi A, and then this program state, C, and what am I going to get? Well, I'm going to get C0 times psi in the A times C0, 0, BC plus C1 times psi in the B times C0, 0, AC. Now, I didn't mention before the normalization condition on this state. I'm going to just squeeze it in down here because the C0, 0 and the C0x are not perpendicular to each other. So the normalization condition here is given by that. Now, we put this in, and okay, this state's a little messy. It doesn't really tell us what we need to know. It certainly suggests that kind of the right thing is going on because the first part has the quantum information in the A line, the second has it in the B line. So what we're going to do is we're going to trace out 2 out of the 3 qubits. So for example, we'd like to look at what's the A qubit going to look like. So what I'll do with that means I will trace out the B and C qubit. And if I want to find out what the B qubit's going to look like, I will trace out the A and C qubits. So I'm going to spare you those calculations, and I'll just give you the results. So what that means, I'm going to take these states and form density matrices, and then I'm going to trace out the parts that I want. So let me call this whole thing, just to be, I'm going to call this capital psi A, B, C, all right? So row A, which is going to be the state of the A qubit, and let me put an out up here because this is the output. So that is going to be equal to the trace over B and C of psi ABC. I'll just write the ABC once. Psi. Okay, so I'm tracing out the B and C qubits. So what do I get? What I get is that this is equal to C0 squared plus C0 C1 times psi, okay, plus C1 squared over 2 times the identity operator acting on the A qubit. So you can see the form of this is that I have what I want, the first term in front, because that now contains information about psi. And then the second term is just an identity, which I can just view as noise. So this is where the imperfect copying comes in. So it copies some of the quantum information about the state that I'm trying to copy, but it's going to add noise to it. So it's going to be a noisy copy. Now, if I do the same thing for B, so I'm going to B out, and this will be B. Okay, same kind of thing, trace, but now we're tracing over A and C, psi, ABC, psi. And in that case, what I'm going to get is, it looks rather similar. It's going to be a C1 squared plus C0 C1 times psi. And this will be in the B psi here. And then we're also going to have noise. This will be identity in the B. Usually we would like the clones to be the same. So that means that what we should do is we should choose C0 equal to C1. So clones same. And if you look at the normalization condition, which is down here, so if they're each equal to 1 over square root of 3, that's going to work, because that would give me 1/3, 1/3, and 1/3. So we choose and then what does that give us? Well, that gives us that psi A out equals okay, so where did that come from? Well, first of all, let's look at what we have down here. If I put in 1 over square root of 3 for C0 and C1, down here, for example, this would become 1/3 plus 1/3. That'd be a 2/3 psi, and then this would be a 1/6 I sub A. And I can write I sub A in a different way, which will give us this expression. So as I said, we have here a 2/3 times psi, and then a 1/6 times I sub A. The I sub A I can write as psi A plus psi per A psi perp. So psi perp is just the state perpendicular to psi. We're talking qubits here, so there is only one state perpendicular to psi, so that determines psi perp uniquely. So if I write I sub A in this way, what happens? So remember what I said, that this coefficient in front became a 2/3, and then this became a 1/6. So I have so I have 2/3 of psi plus 1/6 times this. So 2/3 plus 1/6 on the side gives me 5/6, and then I'm left with a 1/6 psi perp. All right, so that's where this expression comes from. So both of the clones have 5/6 part of psi and 1/6 part of psi perp. And that gives us that the fidelity of the clones is just equal to 5/6. So we get two clones, each with fidelity of 5/6, which is not too bad. And they are approximate copies. They are not exact. They're noisy. And because they have some of the perpendicular, the state perpendicular to psi in them. But that is, in fact, the best you can do in making two equal clones for qubits. And you can get a 5/6. This is actually something that can be used. It's a good eavesdropping strategy for certain kinds of quantum cryptography. The idea being that Alice sends Bob a qubit and Eve wants to find out what it is. She can take Alice's qubit, approximately clone it using this thing, and then measure her clone and then send the other one on to Alice. And that turns out to be a reasonably good cheating strategy for Eve. It will be detected. The quantum cryptography will actually tell that there's something funny going on, but this tends to disturb things in a way that is not terribly great. So it's harder to detect than some other cheating strategies that Eve might like to use. Now, the last thing we're going to take a look at is what happens to qubit C? And you'll notice I haven't mentioned the U0 gate at all. So that's what we're going to do next.